Hi, I am Sanjay Patel. In this video, we are going to discuss problems on the ratio test and the root test for convergence and divergence of infinite series. So first of all, let us quickly recall what are these two results. So the ratio for a given series, say sigma n of positive terms, okay, where n is equal to 1 to infinity, or you can take n is equal to 0 to infinity also. So there are two tests. One is the ratio test. In the ratio test, what we do is, given the series sigma n, we find the nth term of the sequence an, and then we take the ratio, say an plus 1 and an. And then we find the limit of this ratio as n tends to infinity. And suppose this limit exists and it is equal to the number L. In the root test, what we do is, for the root test, we find the nth root of the nth term of the sequence a, and that is, we find an raised to 1 upon n, and then take the limit of this as n tends to infinity. So given the series sigma an, we find the nth term an, and then we take the nth root of an and take the limit of this. And suppose this limit exists, n is equal to L. Okay, so this is to be done first in both the theorems, and then depending on the value of L, we have the three conditions. If L is less than 1, then the series sigma an is convergent. If L is greater than 1, then the series is divergent. For L greater than 1, sigma n is divergent, and for L is equal to 1, the test fails. The test fails means we have to find some other ways to discuss the convergence. So we can check for L equal to 1 separately. Okay, and these conditions are for both the results. So whether we apply the ratio test or root test, if the limit is L, then for L less than 1, we will get sigma n convergent. For L greater than 1, sigma n is divergent. Okay, so let us take examples based on these two theorems to understand how to apply these results. So examples. Our title is to discuss convergence of the following series. Discuss the convergence of the following series. So first example, I am considering the series 1 factorial, 1 upon 1 factorial plus 3 upon 2 factorial plus 5 upon 3 factorial plus and so on. Now the main thing is when to apply which test. There is no rigid rule, but still for understanding purpose, you can remember that whenever we are having say factorial terms or some simple polynomial type of terms, it is better to use the ratio test. Okay, but when we have something raised to n or n square, like say 1 plus 1 upon 2n raised to say n cube, this kind of nth term is there for a given series, then we apply the nth root or the root test. That means for something raised to n, that type of exponential functions or terms, we are going to use the root test or the Cauchy's root test. So let us solve this. Here the given series, we always write like this. If the given series is sigma an, where n is equal to 1 to infinity, is given by, you can first write the nth term by observation. See, the numerator is 1, 3, 5, 7 and so on. So they are all odd numbers, and the first term will be, the general term for this numerator is 2n minus 1. For n is equal to 1 to infinity, you can verify for n equal to 1, you will get 2 into 1 minus 1. So it is 1. And the denominator is simply n factorial. It is very simple. Okay, so thus we have an is equal to 2n minus 1 upon n factorial, and therefore an plus 1 is obtained by replacing n by n plus 1 everywhere in this expression. So 2 into n plus 1 minus 1 upon n plus 1 factorial. Now, as I told you, whenever we have factorial, we always try to use the D'Alembert's ratio test. Okay, that is the practical form of the D'Alembert ratio test. So we are finding an and an plus 1. Now we will take the limit of this ratio. Or you can first simply find n plus 1 upon n and then take the limit, whatever is you find convenient. So consider limit n tends to infinity of the ratio an plus 1 upon an. So that is equal to limit n tends to infinity. An plus 1 is this, which I am writing 2n plus 1 upon n plus 1 factorial, because you know this is same as 2n plus 1 upon n plus 1 factorial on simplifying. This into 1 upon an. We want n plus 1 upon an means n plus 1 I have written here, and 1 upon n means we have to take the reciprocal of this an. So that is n factorial upon 2n minus 1. N factorial upon 2n minus 1. Okay. Now we have to find the limit of this ratio. It is very simple. So this is equal to limit n tends to infinity. Limit n tends to infinity. Here this n factorial is 1, 2, 3 up to n, and this is 1, 2, 3 up to n in n plus 1. So 1 to n will be cancelled, and what you will get is 2n plus 1 upon 2n minus 1. This I am writing as it is into 1 upon n plus 1. Okay. So when you cancel these two, you will get only 1 upon n plus 1. Because something like say 8 factorial upon 9 factorial. So 1 to 8 will be cancelled. That product will be cancelled, and what we will get is 1 upon 9. So this is equal to limit n tends to infinity. This we can divide every term in the numerator and denominator by say n. So 2 plus 1 upon n, 2n upon n plus 1 upon n. And here also I am dividing every term in the denominator by n. So it remains same thing. Okay. This into 1 upon n plus 1 as it is. Now taking the limit, we know as n tends to infinity, 1 upon n tends to 0. So these two terms tends to 0. And again 1 upon n plus 1 also tends to 0. So what you will get is 2 plus 0 upon 2 minus 0 into 0. So that is equal to 0. And this is the value of the limit L. And according to our result, whenever L is less than 1, the series sigma n is convergent. In both the cases, whether you apply ratio test or root test, the result is same. If L is less than 1, sigma n is convergent. For L greater than 1, it is divergent. So here we are getting the limit of the ratio n plus 1 upon n as L, and this L equal to 0 is less than 1. Therefore, by the ratio test, the given series sigma n is convergent. Okay. So whenever there is factorial or some polynomial type of expressions, we always use the ratio test. Let us take the next example, number 2. So next example is say 1 factorial upon 2 plus 2 factorial upon 3 square plus 3 factorial upon 4 cube plus 5 factorial upon 5 raised to 4 and so on. We want to discuss the convergence of this series. So first of all, you must write the nth term. So here, the given series sigma n, you can write as sigma. You observe the numerator here, 1 factorial, 2 factorial, 3 factorial. So in general, we can write it as n factorial. The next nth term will be n factorial. In the denominator, we have 2 raised to 1, then 3 raised to 2, then 4 raised to 3, and so on. So the base starts from 2 for n equal to 1 to infinity. When n is equal to 1, we want 2. For n is equal to 1, we want 2. So we have to add 1 to it. So n plus 1. Okay. We want 2. So n plus 1. And that raised to 1 means that raised to n. So that will be the denominator, n plus 1 raised to n. You understand this? So the base remains 2, 3, 4 and so on. For n equal to 1, when you start for n equal to 1, we want 2. So I must write n plus 1 here to get 2. For n equal to 2, we will get 3. Now you can verify. And the powers, which starts from 1, 2, 3 and so on. So we must write n here in the exponent. So therefore, we have an is equal to n factorial upon n plus 1 raised to n. And whenever there is a factorial, we always try to apply the D'Alembert ratio test, the limit form of the D'Alembert ratio test. So an plus 1 is obtained by replacing everywhere n by n plus 1. So n plus 1 factorial upon n plus 2. N is equal to n plus 1. If you substitute, you will get n plus 2 and the power will be n plus 1. So therefore, the limit will be, the limit of the ratio of an plus 1 and an is equal to limit n tends to infinity. So we always write an plus 1 first as it is, that is n plus 1 factorial upon n plus 2 raised to n plus 1 into, we want divided by an, that is 1 upon an. We always have the reciprocal of this by writing multiplication sign here. So n plus 1 raised to n upon n factorial. Okay. So what remains is just to find the limit of this sequence. So this is equal to, now we just check this. This is n plus 1 factorial and this is n factorial. So this will be cancelled and you will get only n plus 1. So limit n tends to infinity, n plus 1 into n plus 1 raised to n as it is. And this denominator, which is n plus 2 raised to n plus 1, I am writing as n plus 2 into n plus 2 raised to n. This is n plus 1 raised to, n plus 2 raised to n plus 1. Let me write properly. This is plus 1, n plus 2 raised to n plus 1. So I am separating this and we can write it as n plus 2 into n plus 2 raised to n. Now simplifying, this is equal to limit n tends to infinity, Here I can divide numerator and denominator both by say n raised to n. Okay, or rather n raised to n plus 1. Let me explain this way, n plus 1 into n plus 1 raised to n. So I am dividing this by n raised to n, and I am also dividing the denominator by n plus 2 raised to n. The reason is I want to apply, it should be n plus 1. I am dividing numerator and denominator every term by n raised to n plus 1. So divide numerator and denominator by n raised to n plus 1. Because we want to apply that result, as this is n plus 1 raised to n, we want to use this result to find the limit. Limit n tends to infinity, 1 plus 1 upon n raised to n is equal to e. This we are going to use here after some simplification. That you can see in a moment. This is equal to limit n tends to infinity. Now this is n raised to n plus 1. So 1 n I am giving to the first n plus 1. So I can write it as n plus 1 upon n, and this I can write as n plus 1 upon n raised to n. This n raised to n plus 1 we have written as n raised to n into n. This n we are giving to the first bracket, and the remaining n raised to n we are giving to the second bracket, that is n plus 1 raised to n. The same way we can do in the denominator also. this is n raised to n plus 1. So n will divide here and write it as n plus 2 upon n. It is simple multiplication properties. So n plus 2 upon n raised to n will be there. Okay, so everything remains as it is. So this is equal to limit n tends to infinity. You can rewrite this as 1 plus 1 upon n. This I can write as 1 plus 1 upon n raised to n. Denominator I can write as 1 plus 2 upon n and 1 plus 2 upon n raised to n. Okay. So for all the brackets, you can find the limits very easily except this special one, because that result says whenever limit n tends to infinity is there, what we should have is 1 plus 1 upon n raised to n is equal to e. So this denominator, that is whatever it is tending to infinity, and we have this reciprocal of this 1 upon the denominator in the power. What do we have here is limit n tends to infinity 1 plus 2 upon n raised to n. Okay, so this n tends to infinity and we have 2 upon n. So I want the reciprocal of this here. This I can write as limit n tends to infinity 1 plus 2 upon n, and here I should write n by 2 so that I can apply this formula. But there is no n by 2 here. To maintain the same expression, we also take the square so that 2 gets cancelled and you will get the same thing. Okay, so that step is to be done, and then we can take the limit of this ratio. So this is equal to limit n tends to infinity. All other terms I am writing as it is. Okay, upon 1 plus 2 upon n into 1 plus 2 upon n raised to n by 2, and this raised to 2. Okay, so this is an important step. And now we can take the limit and write this limit as n tends to infinity, 1 upon n tends to 0, 2 upon n tends to 0. So 1 plus 0, okay, and 1 plus 1 upon n raised to n, this tends to e. Then 1 plus 2 upon n, that tends to 1 plus 0. And this 1 plus 2 upon n raised to n by 2. So you can think this as, say, 1 plus 1 upon k and raised to 1 plus 1 upon k raised to k, and that gives you e. So the limit of this is e squared. Okay, because 1 plus this and the reciprocal. So 1 plus 1 upon n raised to n. We have the same kind of expression here. So this is equal to 1 upon e. Okay, and now you can see what is the value of e. You know that e is equal to 2.7182 etc., and which is greater than 1. So therefore the reciprocal 1 upon e is less than 1. So this limit is less than 1. This limit is less than 1. Okay, and since the limit of an plus 1 upon an is less than 1, we can say that the series is convergent. So therefore by the ratio test, sigma an is convergent as L is less than 1. Okay, as L is less than 1. Let us take the next example. Say number 3. Consider the series sigma 1 plus 3 upon n raised to n square. Okay, so whenever we have this kind of expression, something raised to n, means that n or n square or n cube appears in the power, we'll generally apply the Cauchy's root test, because it reduces this power. Suppose if you take the nth root, this becomes n, then we can think of some standard results to find the limit of the nth root of an. So here sigma an is equal to sigma 1 plus 3 upon n raised to n square. Okay. So what is an here? So an is 1 plus 3 upon n raised to n square. And therefore, limit as n tends to infinity, an raised to 1 upon n by the Cauchy's root test, you must take the nth root of the nth term an. What you will get is 1 plus 3 upon n raised to n square, and this whole raised to 1 upon n is to be taken. Simplifying, what will be the next step is this 1 n will be cancelled, and what you will get is 1 plus 3 upon n raised to n. Now you know that formula, limit n tends to infinity 1 plus 1 upon n raised to n is equal to e. So we want to use that here. And here we have 1 plus 3 upon n. So we should have the reciprocal of this term here in the power. Then we can write directly the limit of this thing is e. So to bring that reciprocal in the power here, what we should do? We must divide this n by 3. So we have the reciprocal. But in order to keep the same expression, when we divide by 3, we should also multiply by 3, and that 3 we can write like this. So n by 3 into 3 is only n. So this will not change. Now as n tends to infinity, this bracket 1 plus 3 upon n raised to n by 3 is standing to e. So the limit of this term will be e cube, because limit n tends to infinity, 1 plus 1 upon n raised to n is equal to e. Okay. Again, you know that the value of e is greater than 1. So e cube is also greater than 1. So I can write here, this is greater than 1, because the value of e is 2.718 and so on, and which is greater than 1. So e cube is also greater than 1. Okay. So what is the conclusion? We have proved that limit n tends to infinity of an raised to 1 upon n is equal to e cube, which is greater than 1. So by Cauchy's root test, therefore, by Cauchy's root test, this series sigma n is divergent. This series is divergent because the limit L is greater than 1. Okay, so it is very simple to apply the Cauchy's root test. Okay, let us take a similar problem and apply the Cauchy's root test. So next example, number 4, sigma, say 1 minus 2 upon n raised to n. Let us consider 1 minus 1 upon 2 raised to n, 1 minus 1 upon 2n raised to say n square. Okay. We want to discuss the convergence of this. Again, note that this n square is there in the power. So we'll try to apply the Cauchy's root test. So here, note that the series given, sigma n, is sigma 1 minus 1 upon 2n raised to n square. So therefore, the nth term is 1 minus 1 upon 2n raised to n square. So therefore, the limit of the nth root of an, that is limit n tends to infinity, an raised to 1 upon n, will be limit n tends to infinity 1 minus 1 upon 2n raised to n square, and this raised to 1 upon n. So this 1n will be cancelled, and what we'll get is limit n tends to infinity 1 minus 2 upon n raised to n. Again, it is of that standard form. So we should have the reciprocal of this thing with the sign. We have the result, say limit n tends to infinity, 1 plus 1 upon n raised to n is equal to e. Okay, so there must be a plus sign here, but here we have minus sign, so we'll adjust in this manner. It is very easy. Limit n tends to infinity. What I will do is I can write 1 plus minus 2n, or simply write directly 1 minus 2 upon n, and take the reciprocal of minus 1 upon 2n, that is, we should have minus 2n there. So let me write minus 2n here. So we get the reciprocal of this term. You can think 1 minus 2 upon 1 minus 1 upon 2n as 1 plus 1 upon minus 2n. So we have the reciprocal of 1 upon minus 2n as minus 2n in the numerator, in this power, not in the denominator. So in the power, and since we do not have minus 2 here, let us divide it by minus 2. That is, take the power raised to minus 1 by 2. So if you simplify this, again you will get the same expression. So there is no change. Now this is in the standard form, 1 plus 1 upon k raised to k, because you can call this minus 2n as k. So what you will get is 1 plus 1 upon k raised to k. You can call minus 2n as k, and then we can write 1 plus 1 upon k raised to k. So as k tends to infinity, because as n tends to infinity, k tends to infinity, and then 1 plus 1 upon k raised to k is e. So this is equal to, the limit of this square bracket is e, and then raised to minus 1 by 2 is there. So that means the value of this limit is 1 upon e raised to 1 by 2, that is nothing but square root of e. So it is 1 upon root e. Okay. And the value of 1 upon root e is less than 1. This is less than 1. This limit L is less than 1 because e is greater than 1. Okay, so 1 upon root e is obviously less than 1. And therefore, by Cauchy's root test, we can say, therefore, by Cauchy's root test, you must write that which test you are applying. By Cauchy's root test, the series sigma n is convergent, because the value of the limit L, that is 1 upon root e, is less than 1. Okay. So we have solved this fourth problem. So we have seen two problems using the ratio test and two problems using the root test.